Alright, Mrs. Howard's chemistry class, we're still in Unit 10. This is Part 3, Heat and Thermochemistry, and another wonderful cartoon, and this one is by T. McCracken, McHumor.com, which of course is just great. Alright, specific heat. Letter D on your notes, specific heat. Specific heat refers to the fact that different things warm up and cool down at different rates. So, why is it that different metals, heat up and cool down faster than, say, plastic? Well, they attribute it to something called specific heat capacity. So if you feel like your desk at school, if you put your hand on the aluminum, the metal part of it, and also a hand on the plastic part of it, then it feels like the aluminum is a lot colder than the plastic. And it's not so much that they're colder. I mean, technically, they're the same temperature. They've been in the same room all year long. It's that the aluminum feels colder to us because it changes temperature faster and it's absorbing the heat out of our hand. The plastic doesn't change temperature as fast, and so it's not sucking the heat out of our hand as fast or as quickly. Water, dirt, those also are things that alter in how quickly or how slowly they can heat up and cool down. So the specific heat of a substance is the amount of heat required to raise the temperature of 1 gram of that substance by 1 degree Celsius. Okay? Let me say it again. Everything has to be measured. So you have 1 gram, you measure out 1 gram of the substance, and you figure out how much heat does it take to raise it 1 degree Celsius. So it's very, very specific. Now you can think of that specific heat as kind of like thermal inertia. All right, let me backtrack and do a little physics. Inertia is the resistance to a change in motion. So if I try and push your desk with you in it across the floor, I'm going to have a little bit of difficulty with that because if it's stationary, I'm going to have to really put some force into it to get it to change its motion. So how much force do I have to put into it to get it to change its motion? We talk about that in terms of inertia. Well, you can kind of think of that as specific heat as thermal inertia. How much energy do I have to put into it to get it to change temperature? Right? So you can kind of, sort of, think of it as a resistance to a change in temperature, thermal inertia. The greater the specific heat of something, the greater the thermal inertia, or the greater the resistance to a change in temperature. If it's got a greater specific heat, you're going to have to put more energy in it to get it to change temperature. All right, so the specific heat for water, and specific heat is usually designated as a lowercase letter c, is 4.18 joules over gram degree Celsius. So it's kind of a weird unit of measurement. That's a really high number. Okay, I know it doesn't look like a lot, but compared to other things, water has a very, very high specific heat. That means for us that water doesn't change temperature easily. We really have to put some energy into it to get it to warm up. And it takes a long time for it to cool off too. And because of that, it has a huge effect on the climate. Think about how much water is on the planet. And it has a huge effect on the climate because when the water slowly heats, like the ocean, or any large body of water slowly absorbs heat from the sun during the day and finally heats up, and then at nighttime it slowly gives that heat off. So it actually keeps things a little bit warmer for longer. It keeps it more temperate. That's why over on the West Coast in California, they don't see a lot of snow along the coastline at all. You know, if it snows for December, they're just shocked. And we have some calculations. All right, so here's our big equation. You'll see this on the tax test. The equation is written on the back of your periodic table. So Q, and that's the quantity of heat, Q is equal to MC delta T. Every time you see that delta T thing, it just means change in. So let's look at that. Q is the quantity of heat, and we usually measure it in joules or calories, one of the two. M is the mass in grams, has to be in grams. C is the specific heat of a substance, and it's got this weird unit of measurement, a joule over a gram degree Celsius. So it's in grams, and it's in joules, so we usually have to keep it that way. If we want it in calories, then we're going to have to make sure that we adjust it and use the right units of measurement. And then lastly, you have delta T, and that's just the change in temperature. And the change in temperature, it's not always final minus initial. You have to do the change in temperature, the bigger number minus the smaller number, so you're not dealing with negative temperatures at all. So the bigger number minus the smaller number. It's the change in temperature. Okay, so there it says it right here. It says T final, TF minus T initial, TI. In reality, it's the larger temperature minus the smaller temperature. All right. If the temperature of 34.4 grams of ethanol increases from 25 degrees Celsius to 78.8 degrees Celsius, how much heat, that's Q, will be absorbed if the specific heat of the ethanol is 2.44 joule over gram degree Celsius. So we have to write the equation, write the numbers in the equation, draw a box around your answer. So what's our equation? Q is equal to MC delta T. Write the numbers in the equation. We don't know what Q is. The mass, it says right here, the mass is 34.4 grams. The C, it gave it to us. The specific heat is 2.44 joule over gram degree Celsius. And the change in temperature, well, 78.8 minus 34.4, that gives us the change in temperature. So you have mass times C, the specific heat, times the change in temperature. You pop that into your calculator and you find out that you've got 4,515.76 joules of energy that's absorbed. Okay, next one. 4.5 grams of a gold nugget absorbs 276 joules of heat. What's the final temperature of the gold if the initial temperature was 25 degrees Celsius and the specific heat of the gold is 0.129 joule over gram degree Celsius? All right, write the equation. There it is. Put the numbers in the equation. So we've got the mass, 4.5 grams. Grams is mass. And then it says it absorbs 276 joules of heat. That's Q. Q is heat. We have the initial temperature is 25 degrees Celsius, and we have the specific heat is 0.129. So we plug the numbers into our equation, and you notice that the only temperature you don't have is that big T right there. So now all you have to do is solve the equation. You've done these types of equations in your algebra class, so it shouldn't be a problem to you. So 4.5 times 0.129, yeah, and then 276 divided by that answer, and then you're going to add in the 25 degrees Celsius to it. So here we go. So 4.5 times 0.129 equals 0.58 joules over degrees Celsius times TF minus 25. We're going to divide out that 0.58 joules. So now we have it narrowed down to TF minus 25. To get rid of that, we want T by itself. So we're going to add 25 to both sides, and we get 450.8 degrees. So what's the final temperature of the gold? It's 450.8 degrees Celsius. That's the final temperature. That's pretty stinking hot. So 276 joules is a lot of energy. We have a multitude of equations for us to work on in class. Yippee! Oh! And to finally leave you here this evening, this is the end of part 3, and I'll leave you with a note. Be ready for some work in class.